Oh, hi there. Welcome to Groundwork, a series about how each biome contributes in its own way to the stability, biodiversity, and beauty of the planet. I'm Ben Rankin, and today I want to show you why wetlands like these are so important, how they can help stop climate change, and why they're just plain cool. Where I'm standing now is a wetland, and you can tell because there's land, and it's wet. But wetland is an umbrella term, so let's break it down into the four main types. So there are swamps, marshes, fens, and bogs. And those are kind of categorized into two subcategories, with swamps and marshes and fens and bogs. I live in Florida, so we're going to start with swamps and marshes because boy do I have easy access to them. Where I'm standing now is Weeden Island Preserve, and so these waters are fed by the Tampa Bay, which is part of the Atlantic Ocean, in a roundabout way. Now I'm standing a couple hours north at Rainbow River. The water here is fed by a freshwater source. It's fed by Rainbow Springs. Both of these are categorized as swamps and marshes because they are fed by surface water. Surface water is runoff, rivers, lakes, pretty much any water found on the surface as opposed to water in the ground or rainwater. So, we have it narrowed down to swamps and marshes, but how do you tell the difference between the two? Well, swamps are dominated by woody plants, like trees and shrubs, whereas marshes are dominated by grasses and other soft plants. The term for that is herbaceous plants. Cool. Before we move on, it's important to note that even within these subtypes, there are kind of subcategories of both swamps and marshes. Down here in Weeden Island, the waters are fed by those salty tidal waters that we talked about earlier. So, coastal ecosystems like this will often be categorized as mangrove forests, also called just mangroves, or they'll be called salt marshes. Back here at Rainbow River, this is just going to be a swamp or a marsh, though it could also be called a freshwater swamp or marsh. Alright, now we can move on to bogs and fens. So bogs and fens are not defined by their source of water, although that is important, and we'll get to that. But they're defined by the fact that they are peatlands. Peat is basically all the partially decomposed organic matter, mostly from plants, that settles down at the bottom of these wetlands. You see, the soil and water conditions in peatlands really slows down the decomposition process. So when organic matter comes in and settles down, instead of getting broken down, it just builds on top of itself. And that results in meters-thick layers of peat that forms the base of bogs and fens. Okay. So what's the difference between the two main types of peatlands? Well, here we get back to the source of water being important. Bogs are primarily fed by rainwater, and why that's important is that rainwater has already been naturally filtered by the water cycle, so it's pretty lacking in nutrients. And bogs aren't getting their moisture from any other source, at least not in any significant portion, it's just the rainwater. So, the soil in bogs ends up being pretty low in nutrients. So the soil and water condition in bogs is also very acidic, and that's because of the sphagnum mosses that grow on the bottom. Between that, with the high acidity, and the low nutrients, it's hard for a lot of plants to grow here. But when we get to the biodiversity section of the video, we're going to talk just a bit about some of the cool adaptations plants have undergone to be able to grow here. But for now, we've got to move on to our last type of wetlands, fens. Like bogs, fens are peatlands, and they're also fed by rainwater. It's not like they're covered by a big old roof. But the key difference is that they're also fed by water from the ground. And groundwater is really rich in minerals and nutrients because it comes from the ground, where all the minerals are. So the main difference is that even though fens have sphagnum mosses and peat, that minerals and nutrients brought in by groundwater significantly affects what types of plants and animals can live there. Okay, quick recap. Swamps, fed by surface water, dominated by woody plants. Marshes, fed by surface water and dominated by herbaceous plants like grasses. Bogs, peatlands, fed by rainwater, high acidity and low nutrient. And fens, peatlands, fed by groundwater, more nutrients, less acidity. If you get confused, you can always use this fancy chart I made. Okay, now we can talk about why they're so cool. So there are several ways that wetlands are helpful to us silly little humans. For one thing, they provide food and other resources to local communities and economies. Mangroves especially form a sort of underwater jungle, and that provides a safe habitat and breeding grounds for fish and all sorts of other wildlife. What that means for humans is that wetlands like mangroves make for really good fisheries, and that's especially useful to indigenous peoples who rely on their local wetlands to survive. Second, wetlands kind of act like a sponge. They're really good at absorbing a lot of water. That's part of what makes them a great natural solution for anti-erosion. They act as storm and flood buffers and help protect against sea level rise. Third, wetlands greatly improve water quality. Actually, a lot of studies have been done on using wetlands for water filtration because of the way they naturally create drinking water. You see, as rivers and runoff flow through a wetland, some of that water is going to filter down through the bottom, through the roots, soil, and peat. And when that happens, the roots will absorb a lot of the nutrients and pollutants, and then the sand, soil, and peat at the bottom filter out a lot of the particulates. Remember when I said about 30 seconds ago that wetlands act like a sponge? Wetlands kind of act like a sponge. They're really good at absorbing a lot of water. Well, that can be useful for drinking water as well. Wetlands will absorb a lot of water during the wetter seasons and then release it back in the drier seasons to help stabilize the water table. Hi, it's Ben from the future. We'll meet soon. I wanted to expand on this a little bit more before moving on, so I found this cool study from Louisiana State University in 2004, and it looked at how much money could be saved by using wetlands for water filtration as compared to traditional man-made water filtration plants, and the results were really surprising. So this study found that using the wetlands that are already there in Louisiana for water filtration could save $1.8 million in upfront costs and then another $72,000 per year. And even better than that, dumping like wastewater into wetlands sounds like a terrible idea. It would pollute the wetlands and be bad for them, right? Wrong. Scientists use a fancy term called net primary productivity, or NPP, to describe basically how much plant growth an area produces in a given period of time. And the crazy thing is that it turns out releasing this partially treated wastewater into wetlands can actually boost net primary productivity and help restore the wetlands. Super cool! So what else do wetlands do? Well, they're a trove of biodiversity. A lot of the studies and resources I read in researching this video compared them to rainforests, and rainforests are like the poster child for biodiversity and rich ecosystems. But wetlands are home to all sorts of different insects, amphibians, mammals, reptiles. Take a look at what I found just on my outings for shooting this video. Welcome back. I plan to make a whole separate video on why biodiversity matters, but until then, just look at this. This is so beautiful. This is so cool. Look at all these guys. Now there's one specific class of organism that I want to call out. We mentioned earlier that we talk about some of the cool adaptations that plants have undergone to be able to live in the harsh soil conditions of bogs. And what I was referring to there was carnivorous plants. Carnivorous plants are so cool. They're a great example of biodiversity and evolution filling in a niche. Because remember, the soil conditions in bogs are really harsh. It's very acidic and there's very low nutrients. And that low nutrients thing is actually why carnivorous plants evolved. They evolved to eat insects to get their nutrients because they couldn't get it from the soil. Some of them literally create a vacuum to suck up their prey. That's so freaking cool. Alright, now to the main point of the video. This is how wetlands can help stop climate change. There's been a lot of talk in recent years, especially from the tech industry, about carbon capture, using machines to suck carbon dioxide out of the air. The problem is that natural ecosystems already do that, and they do it better. Plants grow by taking carbon out of the air, They do that, do some fancy biochemistry stuff, and then they use that carbon to build new organic material. Wetlands are especially good at that whole process, and that is for two reasons. First off, wetlands are very productive ecosystems. There's a lot of plants growing, and they're growing fast. Second, because wetlands are waterlogged, that water helps literally keep the carbon down just by keeping it trapped in there, but it also slows down the decomposition process, which would normally be releasing carbon back into the atmosphere. Okay, now let's move on to some fun numbers that support my thesis. So we said that wetlands are both productive and they store carbon, right? Well, that maps perfectly onto the two key metrics that we need to look at: carbon sequestration and carbon storage. Carbon sequestration is how much carbon a system removes from the atmosphere over time, and carbon storage is how much carbon is stored in a system in a given patch of land. Carbon sequestration is the faucet and carbon storage is the bucket. Now, I was doing research and writing for this video, and I know that this section just by nature is going to be throwing a lot of numbers at you. So I was trying to think of how to make it interesting and how to keep up with the numbers, when I realized that I can use a scientist's favorite tool: a tier list. Alright, so let's get started with our poor man's tier list. Before we start, I want to look real quick, point out this reference card in the corner. These are basically fact sheets that are themed as trading cards, and so this reference card will help you decode what these numbers actually mean. They are actually fact-checked and real numbers, but we're just going to treat them as like trading card scores so that we can compare them. We'll start with tropical forest. We're going to start to kind of like give a frame of reference. So we've got solid starting area score, 20. That's 20 million square kilometers globally. That is a lot, especially as compared to the other ones. Their carbon storage score is 21.4, and the sequestration score is 60. Those are really solid numbers, nothing to bat an eye at. You can see that the global scores, so 428 for carbon storage and 1200 for carbon sequestration, those are really high, but a lot of that is boosted by that high area score. They take up a lot of area, so they have high global scores, even regardless of their per square meter scores. Because that's a frame of reference, it's really solid, but we're going to just leave it at B because we're going to see better, we're going to see worse. One more frame of reference thing, we're going to look at cars real quick. Obviously, these are headed to F tier. Cars are the worst. We don't like cars here at Beanstem. They are located globally. And yes, I calculated the per square meter emissions of cars to standardize the unit here. And that is 334 kilograms of carbon per square meter based on the average car size. And globally, cars emit 3.6 billion tons of carbon. They're the worst. They're being banished over here. Moving on to our first actual wetlands. We're looking at salt marshes. Again, that area score is a lot lower at only 0.18, 180,000 square kilometers. We can also see that the storage score is actually a lot lower than tropical forests at 5.5 and only 1 globally. That area score is not doing it any favors there. The sequestration score, though, is almost 4 times tropical forests. Salt marshes are really good at sequestering carbon. That is your takeaway here. Because it's trading blows with tropical forests, I think we're going to put it in the same category. It's got that lower storage score, but that way higher sequestration score. So kind of trading blows there. Moving on to mangrove forests. Again, very similar area score, 0.14. But if we pull up the tropical forests again, we can see that both the storage and sequestration score are way higher than tropical forests. The storage score is 71.4. That's almost 3 times as dense as tropical forests for storing carbon. And it is also almost 3 times as good at sequestering carbon, at least per square meter. If we compare that to salt marshes, we can see that it's way better at storing carbon, but not quite as good at sequestering carbon. So your takeaway here is that mangrove forests are really good at storing carbon. Mangrove forests are well renowned as being very vital carbon sinks because they store a lot of carbon in the ground. We're going to put those up at A tier because the sequestration score is pretty similar to the salt marshes, but the storage score is so much better. Last one to look at here is peatlands. That area score is a lot higher than the other ones we've seen for the wetlands. That is 2 million square kilometers globally. And the storage and sequestration scores are also higher. So if we compare that to our first one, to tropical forests here, we can see that it is 10 times better at storing carbon and about 5 times better at sequestering carbon. So tropical forests, rainforests are well renowned, and they are very vital, important ecosystems. But just looking at these flat numbers, peatlands are incredibly important as ecosystems that sequester and store carbon. Even compared to our mangrove forests up in A, we can see that the storage score is way higher, the sequestration score is way higher. Compared to salt marshes, which are the ones that are good at sequestering, they're still really good at sequestering compared to peatlands, but peatlands still beat them out. The last thing that I really want to point out about peatlands to sing their praise even more is we see that the area score is only a tenth that of tropical forests. And despite taking up only a tenth of the land, they actually store more carbon globally. That global score for peatlands is 469, and on tropical forests it's 428. Similarly, the sequestration score globally for peatlands is really admirable compared to tropical forests. It's about half that of tropical forests, but again, they take up a tenth of the land. So that really helps drive home the point about how important peatlands are as ecosystems for carbon sequestration and storage. Because of those incredibly high numbers, I think we have to put that up here in S tier, where they reign supreme. To kind of drive this point home, it's hard to find any studies that would give numbers as broad as carbon sequestered by all wetlands globally, but these 3 types do account for a lot of it, and combined, these end up sequestering about 81 million tons of carbon per year. And even combined, you can see that these numbers don't really compare to the one I brought up earlier for cars at 3.6 billion tons of carbon per year. So, to give you a better frame of reference, 81 million tons is about equivalent to the yearly emissions of 5.5 million Americans. Or 12.8 million Irish people, which is about 2.5 Irelands. Wait, which Ireland? Okay, moving on. Unfortunately, despite the economic, biodiversity, and carbon capture benefits that wetlands provide, there are some things threatening these ecosystems. Over the last 20 years, we've seen an overall decline in mangrove forests, and that could have some serious consequences for the climate crisis. But what could be causing this? One of the main things is deforestation caused by logging and development. Actually, one of the main causes of mangrove deforestation is aquaculture development, which I don't get that. Because we already talked about how mangroves are great fisheries because of the natural habitats they provide. So tearing down these rich, diverse ecosystems and replacing them with monoculture, man-made fishing facilities is just nonsensical to me. Aside from causing deforestation, urban development can also mean building dams and roads that cut through wetlands. Human infrastructure can change the flow of water to cut off a wetland and effectively dry it out. Another threat is eutrophication from the agriculture industry. Quick rundown on what eutrophication is. When agriculture uses too much fertilizer, it ends up running off into nearby ecosystems like wetlands, lakes, and beaches. That influx of nutrients causes a certain type of algae to have a field day, and they grow like crazy. And then that ends up taking a bunch of oxygen out of the water, which suffocates a bunch of fish, frogs, and plants. Yet another threat is invasive species. Plants and animals get introduced and they don't have enough natural predation, so their populations grow out of control. They outcompete native species and they can turn an ecosystem on its head. But the main thing threatening wetlands is climate change. That's right, we're going back to the climate crisis, baby! I mean, it is right there in the title. Unless it's not, I don't know. I don't know which title's gonna perform the best. So, climate change, we're talking 3 main things. We're talking rising sea levels, natural disasters, and we're talking global warming. First up is rising sea levels. Rising sea levels can inundate wetlands with salt water, and that extra salt can tear through a wetland. Even coastal ecosystems like mangroves and salt marshes can be overwhelmed with more salt than they can handle. Next, natural disasters. Another figure from that same study showed that, quote, approximately 70% of mangrove loss has occurred because of low-frequency, high-intensity weather events such as tropical cyclones. Now, I don't have time to get into it because this video is already longer than I want it to be, but it is well documented that human activity and global warming contribute to natural disasters like these and make them more intense. Which leads us to global warming. Now, there's a few things that global warming does to wetlands. For one thing, it speeds up the decomposition process. If you'll remember, one of the things that makes wetlands such great carbon sinks is that the conditions slow down the release of carbon through decomposition. So when the temperature rises and decomposition accelerates again, wetlands can start to release more carbon than they're capturing. And another thing that global warming does is it melts permafrost in tundra wetlands. And that permafrost is keeping a lot of carbon sealed away. So again, when that melts, we end up releasing more carbon back into the atmosphere. But another thing I found is that global warming and sea level rise can actually temporarily make wetlands more productive. Salt marshes and mangroves, most of them can keep up with some amount of sea level rise, but there's only so much they can do. And we are seeing places where the amount of sea level rise is just too drastic for them to keep up. And it's important to note that these gains are only temporary. There's only so long that we can abuse these ecosystems before they just can't fight back. And the problem is that when we lose wetlands, we don't just lose them as natural habitats and storm buffers and all those good things we talked about earlier. We also feed into a positive feedback loop of ecosystem collapse. What I mean is, we know that wetlands are a great carbon store. They hold a lot of carbon in the soil and under the water. But when that ecosystem starts to collapse, it'll start to release all of that carbon back into the atmosphere, causing more warming, killing more environments, causing more warming. And that principle is why scientists from all around the world are so concerned, and why the UN is sounding the alarms. A quote from the International Panel on Climate Change from last year said that with further warming, climate change risks will become increasingly complex and more difficult to manage. Okay, that was a lot. Let's take a deep breath and move on to some of the more positive stuff and how we can fix it. Sure. The main thing to take away here is that preserving and restoring our existing wetlands is overwhelmingly our best option. It provides the most immediate benefits, it's the most cost-effective, and it keeps humans and animals from being displaced. Outside of that, removing human infrastructure like roads and bridges can help restore and even create new marshes. Another option that addresses sea level rise with that increased salinity is literally just flooding wetlands with more fresh water to push that salinity out. And in a similar vein, irrigation and dredging can help restore the natural water flow of a wetland. I watched a super cool video recently from the excellent channel Mossy Earth here on YouTube. It actually showed this in action. They've worked with local governments and organizations recently to flood a huge patch of wetlands in Slovakia. And they've shown the difference in the environment and the wildlife over the last 2 years that the project has been running. And it's so inspiring. Go check it out. And wetlands can be incredibly resilient. Like we already mentioned, certain wetlands can already keep up with some amount of sea level rise and global warming. And like that Mossy Earth project showed, they can bounce back quickly. This study I found showed that after restoration efforts, all of the observed wetlands experienced rapid growth, with some of them doubling in vegetation cover in only 2 years. And there's a lot of potential. The potential restoration area of mangroves, marshes, and seagrasses is estimated to contribute an additional 229 million tons of carbon per year by 2030. That number does include seagrasses, which we didn't cover in this video, but that figure is also almost 3 times what we calculated earlier for mangroves, salt marshes, and peatlands. The thing is, from my research, consensus among scientists is that governments need to be on board. Policy and regulation from governments is vital to encourage preservation and restoration, and to keep companies and municipalities from developing these areas. To wrap this up, I want to summarize and reiterate. Wetlands are very resilient ecosystems, and they can bounce back quickly from damage done by humans. But the best thing we can be doing is making sure governments are issuing and enforcing policy to protect and preserve these wetlands, to leave them to their natural beauty. And that's it. That's the video. That is how wetlands can help solve the climate crisis. If you're still around watching, genuinely thank you so much for watching. I really appreciate it. This was a very ambitious first project for me, a 30-minute video with multiple locations. It took me about 4 months to make between research, shooting, and editing. And I could not have done this without basically all of my friends. So anyone who helped me work on this, thank you so much. I appreciate it. You can check out the description below will be a link to the beanstem.org post about this. That'll include all the citations, references, B-roll footage credits, as well as a full transcript and just any information that could be useful for nerds who want to learn a little bit more. Speaking of, if you are a nerd who wants to learn a little bit more and you have very similar friends, it would mean a lot for me if you were to share this with your friends. Yeah, I guess that's pretty much it. Thank you again so much for watching, and hope you have a great day.